Next up, we have Vijay from SambaNova. Um,
Hi, folks, this is Vijay.
Hello.
Yes. Hi, Vijay.
Hi.
Yeah.
Can you hear me okay? Can I?
Yes, perfect.
Yes.
Yeah.
And remember, you see the screen, it's, although it doesn't look like her.
Or maybe you could go to the presenter mode. What is?
Am I in presenter mode already or?
No, not yet.
Yeah.
Okay. How do I get into presenter mode? I see.
You can go to the slideshow tab.
Yeah. Let me stop that. And so you're saying in the, oh, you mean on my slides, you're saying I should go and present.
Yeah, that's right.
Yeah, I was wondering if there was something in Zoom I needed to do. Okay. Yeah. Okay.
Yeah, you can click the slideshow tab and then play
Yeah.
from start. Yeah, perfect.
So am I in presenter mode now or am I in the other mode?
Now we can see your slides. Perfect.
Yeah, it looks great from here.
Okay. Okay. Are you able to see one slide or are you able to see
Just one title slide.
one title slide, right? Okay, perfect. Thank you. Because I'm using a dual monitor here. So hello, folks. My name is Vijay Tatkar. I work in the partner engineering organization within SambaNova. I've been at SambaNova for about 5 years now, little over 5 years, and I've been there since the first SambaNova DataScale product, SN10, and we've been there since DOE actually started working on the very first one, right? So we are very privileged to have DOE as one of our first partners and customers there. So very pleased to meet you all. Don't hesitate to ask me questions. What I'm going to do is I'm going to walk through the DataScale SN30 platform that you have access to. And as I do that, I'll also talk about and the next thing that we have announced. So give you a quick overview of what's coming or what we've announced in the last 9 months, right? You don't have access directly to that, but you can get other ways by which you can get access to that, right? So and you are more than free to use those methods. I'll talk about that at the end. So let me just deep dive into it. Before I do, Murli, any other introductions or anything you'd want me to say or anything that you need to add in terms of SambaNova and where we are in?
I think we are good. We can continue, Vijay.
Okay, perfect. Yeah, sounds good. So let me give you a quick overview. So as a startup, it's always good to know where the company comes from, who's founded it and what the founding philosophy is and what it's based on, right? So at SambaNova, we have three co-founders, Rodrigo Liang, Kunle Olekuttan, and Chris Ray. And two of the three, Kunle and Chris, are actually from Stanford. They both teach at Stanford. They have taught at Stanford for over, Kunle has actually taught since mid-90s, and Chris Ray's taught for about 15 years now. So many of their students, many of their graduates are part of the SambaNova workforce as well. And we are very pleased that particularly on the system, on the software side, we are we have the advantage of having folks, some of our brightest folks coming in from Stanford as well. There are other universities, clearly, right? So that are also part of Stanford. So we have a very large alumni within SambaNova from various universities, including Michigan. So SambaNova was formed in 2017 out of research that came from the work that Kunle and Chris Ray were doing on a project called Data Analytics, What's Next, Dawn. So if you want to look up some of the background material, I think that's where you look at it. The whole idea there was that they were in investigating a new domain as AI was emerging as a domain. And they started looking at it from a software perspective, clearly being university folks, and looked at various things within the software and decided that, hey, look, it's not just a hardware problem to accelerate these applications. It's both a combined software hardware problem. So as they looked at it, the solutions that emerged, or the approach that emerged, was a combined hardware software platform, and that's basically what's been our basis for right from day one. So we actually have two products, and but more importantly than the products themselves is the fact that we actually are, as a company, are a company that goes all the way from chips to systems, to software, to models as a service, right? So we provide the entire experience all the way up to solutions. We don't do solutions. We work, or rather, folks like me work with partners to bring solutions to our platform and to develop a larger ecosystem. So let's deep dive into the platform itself. So just remember, as we are doing this, that this is, don't think of hardware in isolation, don't think of software in isolation. This is all a combined product where essentially you start with a model. You look at the model, you kind of analyze the graphs there, and optimize for the components in there, and the components that are needed to be optimized, those are accelerated in hardware, right? So that's the way to look at it, basically, as you look through this. Clearly, software has changed over the last 40 years, 50 years. I have been in the business for over 30 years now, and I started off in C, C++. We did some of Sun's first C compilers back then. And that clearly has changed. All of that was what we used to back then call the von Neumann architecture, or control flow architectures. AI is much more of a data flow problem. And what that means is that two things. One is that applications are not written, they're not coded with logic the way your traditional applications whether you're talking about databases, CRM, HCM, whatever, operating systems, you name it, right? Traditional applications are written that way. Whereas these applications are written more to be data flow applications, that the applications are trained with a lot of data. And so the movement of data within these models, and optimizing that movement is critical to these applications. And that is something that traditional architectures just do not do. Whether you're talking about CPUs or GPUs, they're not designed to optimize for data flows within a model, right? So they're optimized to make instructions go fast, right? So a different philosophy there. Clearly, as you're designing for these, compute is something that has now become more of a utility. It's all based off of, whether you're using TSMC 7 nanometer or 5 nanometer. Pretty much everyone has very similar characteristics there. But memory capacity and memory movement and memory optimization and data optimization are a huge pain point. And what you see happening both within the SambaNova architecture and other architectures that are in the field is how well do these architectures optimize around that, right? So in particular, when you look at traditional architectures, let's say you have a neural network that looks like this, right? It's got a bunch of operators that look like norm, sum, convolution, spool, things like that, right? What we do in a traditional architecture, like a GPU or a CPU GPU combined, is you take the first instruction, you decode it, and if it's a large enough instruction, you send it to a GPU, and then you send all the data that goes with it. That's what you see on the left-hand side. When the instruction is completed, when it's executed, then you take the results of that and put it back into memory, and then you decode the next instruction, and so on and so forth. So that's how you go sort of. It's not necessarily instruction by instruction, but it is more kernel by kernel. So you look at each of these, whether it's convolution, pool, norm, sum, these are all like kernels as opposed to being instructions. So you do a kernel by kernel execution. The problem with doing that is that now you're bottlenecked by all the memory movement, all the data movement that has to happen between a CPU and wherever the memory is held, right? So typically in the case of a GPU, this is why you need HBM memory, because you need something that has high throughput and low bandwidth. On the other hand, what we do is essentially take a graph like you see here, and we basically compile it and we lay it across the chip, right? And that's what you see on the right-hand side there. So our chip is architected to hold the entire model during the time of its execution. So what you see is that the entire model is laid out on the chip, and then the data kind of flows over it. So you get automatic pipelining of the instructions and of the data movement there itself. You get optimization of the of data within the chip itself, so from operation to operation. So the point I made earlier about having data being optimized as it goes through its various steps, that's something that gets achieved here. And then there are other things that fall out as well. So very different ways. So one is a spatial way of doing things. The other is a kernel by kernel way of doing things. Okay. And that's architecturally an important point to remember as well, because there are things that you need to do on the left hand side, for example, like CUDA, right? All the CUDA optimizations are geared to make the operations on the left hand side go fast. On the other hand, there are different things that you need to make operations on the right hand side go fast as well, right? So those are very different design choices in that sense, and now you can see where or what kind of design choices we've made. SambaNova SN30. So let's go to the bottom of the stack, so to speak, right? It starts with a chip. So let's start with that, right? So SN30 is a third generation SambaNova chip. The first one is SN10, the next is SN20, as you might imagine, right? So this is what we call an RDU. So just going back to our previous concept, what we have in the architecture is we have a data flow chip, right? A chip that supports the data flow way of doing things, right? But we also have a chip now that basically is a reconfigurable chip as well. So this chip has, we'll get into some of the characteristics of the chip itself. It has a large amount of compute, clearly at a very global level. That's what you need in AI. You need lots of teraflops, lots of floating point computations, lots of matrix multiplies, lots of other kinds of operations. And these are not necessarily all, you don't need FP64 in the case of AI. Many of these operations are BF16. Today, people are doing things even in FP8. But that precision discussion apart, I think essentially you need a lot of compute, and we have more compute than um, uh, more than enough compute that you can fit on the chip. Okay. We also have a large amount of memory on the chip. We have 640 megabytes of memory on the chip. That's roughly between 10 to 20 times what you find on a GPU, depending on which version of GPU you're looking at. Or it's probably about, could be even up to 50 times more than what you find on CPUs, right? Depending again on what kind of CPUs you're looking at. So a large amount of memory to hold the data that we need, right? So now you understand that we have compute, we have memory that can hold the data that is needed to be processed while it is on there. And then the chips themselves are connected to each other through RDU connect, but we'll get to that, right? So, and we'll get to the 102 kilometers of wire, which is by itself a fun fact. 86 billion transistors, these the current 7 nanometer technology is tremendously good at compressing a large amount of transistors. So as you can see, we have 86 billion transistors there. We'll get to other numbers as we go along. Okay. Deep diving into the architecture, what we really have in the architecture is basically a large number of compute units that we call PCU. Remember, I said this is all based off of understanding what software looks like. And essentially, during the research, when they looked at various kinds of neural graphs, they decompose them into smaller components of what are the building blocks for that. And the building blocks are what we call patterns, and that's where some of the terminology comes here. The compute units are what we call the pattern compute units because of that. And then the memory units are what we call the pattern memory units there. So as you can see, the compute units and the memory units are interspersed with each other. They are connected through these S's, which are the switches that you see here. Okay. So the switches are basically the routers between the data that is found in the memory and compute where the data then gets processed. And basically these are very fast switches that can can route data from in whatever mapping fashion you need, whether it's all to all or all to one to many, all any of those. That's what the switches do. And that's where the 102 kilometers of wire comes. Essentially, on the chip itself, we have metal that basically takes data from one place to another at extremely rapid speeds. So when we say rapid speeds, on chip you can do like petabytes per second kind of thing. So those are virtually eliminating latency for data that is found on the chip itself, right? So that's the whole idea behind it. And then there are interconnectors that go between, that help to connect the chip to other parts, right? In this case, other parts can mean two things. One is that we have a composition where we put many of these chips together. In our case, we put 8 of these chips together in one, what we call a node. Okay. So if you're familiar with the DGX box, that's kind of similar in that sense, topology, where there are 8 of these units that are connected together, right? These are also connected to the outside world as well, right? And the coalescing units help with that top level and inter-chip interconnect as well. Okay. So all of these chips from the ground up are multi-tenant chips. So they are designed, it's a tiled architecture. I should have mentioned that before. It's a tiled architecture. And what that means is that there are, in this particular case, there are 8 tiles, and you can run an application. You can run an application on a single tile if you want to. Okay. So you can run up to 8 of these applications on a single chip. And in fact, as we put multiple of these chips together, you can run many applications on a node itself. Each of these applications, you can have mixed workloads. There's no constraint around what kind of workloads you have. You can do concurrent applications. You can do multi-user applications, multi-tenant applications, all of that. So you have multi-tenancy and multi-user support. And all of this is governed by compilers. I haven't talked about the compiler yet, but this is all governed by compilers. So we'll get into that in a minute. What we do with this is we basically take this and we put it in a platform that's a rack scale platform that we call DataScale. And DataScale is basically a rack optimized platform where everything that you need to make a rack operational is there, right? So we have these compute nodes as we call them, and we have a networking switch on top. We have a management switch on top. Everything about the rack otherwise is pretty standard, right? The form factor is standard. The power requirements are pretty standard. It's air cooled. The networking is standard. We have a switch that is from one of the popular vendors, but you can pretty much architecturally you can use any other switch that you want as well. So pretty much everything else about the boxes, about the rack itself is pretty standard. And what that allows us to do is that because these are standard, there are no special requirements for any data center, which means that when we ship these boxes, these can actually be installed in literally minutes. So within a minute, you can have an entire rack of gear, of AI gear up and running. Okay. And up and running means you can have it up and running, ready for it to import models, ready for you to bring your research to it. Or it could mean things like in cases where we provide the models themselves are up and running, and you can start doing inference on them as well. So in all those scenarios, you can do these what's in a node individually. So there are up to 4 nodes in one rack. There is so you can have a rack that has 1 node, or you can have a rack that has 2 nodes, or you can have a rack that has 4 nodes. I believe the racks that are that you have access to are basically 2 node racks at this point. Murali can probably correct me if I'm mistaken here. Each of those nodes is basically has 8 of these accelerators in a configuration that you see here. The bottom server that you see is basically an x86 server. It's a standard off-the-shelf x86 that's running off-the-shelf Linux as well. So as I mentioned, everything outside of our own IP is industry standard. So there are no special requirements. So what that means is with an x86 Linux host, you can do everything that you can do with a Linux box. You can SSH into it. You can mount file systems. You can run VMs. You can run it in a Kubernetes environment, whatever you want, right? Additionally, each of these contain 8 terabytes of total memory. And what that essentially does is that it allows us to run models that are extremely large, right? So we'll get to that in a minute, but when you have a compiler that can basically lay out a model, not just in one tile, but across tiles, and then also across RDUs themselves, up to 8 RDUs, then you essentially can run very large models. Today in the industry, we haven't found models that are large enough that you actually can't run on an 8 RDU system. So even the largest models today, you can pretty much run on one host. You might need multiple hosts to get like better throughput, or to be able to serve more users, things like that. But pretty much everything that you need to run, you can run on a single node itself. So that's what's in a system here. All of this is enabled through a software stack. And in our case, the software stack for DataScale has 3 components, I would say. Two of them we are going to talk in some detail here. One is what we call SambaFlow, which is a system level stack, which has compilers and runtime and components like those. Then there is a stack that's above that. That's a sort of Samba Studio stack, which has ML ops and things that support ML ops in there. And then there are applications that are written on top where we provide models as well. So we'll talk a little bit about that as we go along. But going back to SambaFlow, so SambaFlow is a framework that basically has components that include a runtime, includes a compiler, includes an SDK. Essentially, it supports standard frameworks like your ML frameworks, such as PyTorch. Okay, and was there a question that was? I'm hearing something in the background. Was there a question in the?
No, I'm not seeing any questions here.
Okay. Okay, that's good. So hopefully you're able to follow along as I'm walking through these slides. So the SambaFlow is the software stack that basically extracts the graphs as I mentioned, and then optimizes them for the RDU, right? So there are the key components. There's a compiler in there. There's runtime in there. There are templates in there. The compilation flow is where you take these PyTorch and through an API, convert it through our own framework that we call Samba, and underneath that is a graph compiler and a kernel compiler that works off of that graph, and then later on decomposes that into various templates and puts the optimized templates around that together, right? So that's the basic architecture around the compiler. We have runtime that basically enables all of this to be run at scale. So compiler has different modes. There's an operator mode, there's a module mode, and there's a full graph mode. I won't go into all the details here. Essentially, as you might know with compilers, there's like different features, different capacity capabilities at all of these. But more importantly, there are different optimizations that happen. One of the key optimizations that you need in AI with AI applications typically is operator fusions, right? So we have several techniques that we use. Some of those could be heuristic, sharding, tiling, things like that, doing section cuts. You can learn more about this as you start developing these applications. All of this is built into the compiler. So the compiler can automatically do these optimizations for you. In addition to that, as I mentioned, the compiler is capable of taking a model and spreading it across 8 RDUs. So you get model parallelism for free as well as part of that. The SambaFlow runtime is again a package that basically operates as an operating system for RDUs, essentially, right? Basically takes the applications that you've compiled and then makes those available for the RDUs themselves. It's supported on the various Linuxes, and it manages the compute, the memory, and the IO for during model execution itself. So again, I don't think I should get into all the features here. I might run out of time seeing that I want to get onto another section where we talk about what's the latest from SambaNova. So here in DataScale itself is built with enterprise features in mind, multi-tenancy, multi-users, as you saw in the past, with the data flow kind of philosophy of an architecture behind it. That's the key driver. But there are several features in DataScale that are enterprise-free features. You can do distributed data parallel training, like you can do for many platforms in the industry. There are system RAS features that are there that are available, hardware fault error management features that are there, application debugging, diagnostic tools that are available for doing things like observability, for performance tuning, things like that. So all of these are available as part of the Samba Flow package that you have on the system itself. Now, what I want to do is I wanted to spend a few minutes to talk about where the market is going, right? So I talked about what we have with SambaNova and what's unique about SambaNova in that sense. So yes, the performance is very good. The capabilities are very high. You can run extremely large models. What we've done is essentially taken that and we've created a Kubernetes Kubernetes-like management and orchestration platform. And what we do is we also deploy models as a service on top of that. The DataScale platform is what we call a model development platform. So it's for model research, for model development, for model training, things like that. And much of the industry is also worried about, okay, now I have that, but there are also a large number of models that are out there. How do I do inferencing, right? I need a good inference platform. So we have an API-driven inference platform as well. And in addition to that, what we've also built, so not only do we deliver popular large language models like when you start looking at models like Llama or Falcon or Mistral or Bloom or any of these large language family model families, we deliver these pre-compiled, we deliver these pre-optimized, we deliver these pre-trained in the box. What we've also done is we now have an architecture where we put many of these together under what we call a composition of experts. Essentially, from the outside world, if you're familiar with ChatGPT and you're familiar with Gemini, right, these are basically very large language models that are over 1 trillion parameters long. So we similarly have from the outside what looks like a 1.3 trillion parameter model. Underneath that, it actually is based off of a very large number of experts. The first version was based off of 54 experts. The next version that's just coming out now is based on 92 experts. We support 30 different languages. There are 10 different domains. Mind you, from the world outside, as they look at this model, it looks like one single model. It's not a monolithic model, so we'll talk a little bit about that. But it's for the rest of the world, you are kind of communicating or you're interacting with it like it is one model. Okay? It's the single model is capable of taking on diverse set of tasks, and it's built out of 7 different foundation architectures. So what we have done is what's underneath the covers is basically that there is one the composition is basically a router model, and underneath the router model we have 54 models that are experts in their own domain. So whether the domain is physics or chemistry or math or whether it's medical or whether it's coding, you name it, right? We also support, like I showed you, a large number of languages as well, right? Including low resource languages as well, right? For which we have created some really good specialized models there. All of these models are open source, so they're based off of open source models that are out there. All the work that we have done is also open source, which means that all the work that we do, we also put back into the industry as well. So all of these are available. That allows us to provide a model that actually has the capability of a GPT-4 or a ChatGPT, if you will, right? So at that level. So the capability and what we have shown in the recent times is that on our platform, we are able to have performance that's like between 10 to 15 times more than what you can get on a GPU, right? Whether it's a GPU or an OpenAI based offering, we have the capability of doing that today. Okay, so there is a router underneath that. All of this is based on the 4th generation of the chip, which we didn't talk about. Okay, so the 4th generation has many of the same characteristics the 3rd generation has, but it also has a very interesting data flow memory tiering. That is a different architecture around memory that makes it very attractive. All of this is you can get to all of this through SambaNova's own site. So if you go to sambanova.ai, you can get to something called the Sambaverse, where you can try out these models, or you can try out the various apps that are there, or you can try out the speed that I talked about, which was like, you can get 10 times, 8 to 9 times faster than GPUs, or 15 times faster than a GPT model, right? All of that you can try for yourself. So that's my introduction for SambaNova for folks. I'll kind of pause here, and I know I've gone 2 minutes over time. I appreciate the attention and the patience that you've shown. Thank you. Murli, any questions or anything you would want me to address?
Thank you so much, Vijay. I'm just looking. I don't see any questions in the chat. Yeah, but I think you've kind of covered the hardware and software stack, and that's perfectly suited for this tutorial. And again, for attendees, if you have any questions, please feel free to ask them.
Yeah, you can get more information from our documentation as well as from our support portals, as well as our regular support, regular portal as well, regular site as well. So feel free to register yourself, try out some of those things there. Thank you.
Thank you so much, Vijay.
Yeah, thanks for having me, Murli. Appreciate that, folks.